All right, line A5, learning task number 6. We're going to start talking about the effects of having opens, which is going to be a circuit that is not complete inside of three-phase circuits, whether that's going to be inside of a Y circuit or inside of a delta circuit. And we're going to go and look at them individually, one by one, but we're going to start with the Y circuit over here. And inside of your book, they show you the effects of an open. They say call this thing single phasing resulting from an open line inside of a Y type of circuit. And then they go and tell us, inside of an example, that we're going to go and get strange voltages that are going to go and happen across our different components anytime that we go and have single phasing. Let's just talk about that real quick, and then we're going to demonstrate how exactly that's happening. First of all, we have got a 120 208 volt type of system, which means that we have got a line value, we've got a phase value of voltage, and we have got, therefore, over top of each of these, 120 volts over top of my individual loads is what I would normally be seeing over here. Line to line, that I would go and have 208 volts. But then what's going to go and happen is that we're going to go and lose a line. In this case, we're going to lose a line through an open fuse. Something has blown inside of there. And as a result of that, all of a sudden, the values of voltage are going to go and change across some of our remaining ones. This one over here is going to go down to 0 volts. And these two over here, if I measure across them with a meter, are no longer going to go and be 120 volts. They're going to change to another value of voltage. They show it as 104 in the next example. And we're going to explain where and how that is actually happening. And it's best off to actually be explained through visuals. Looking at these pictures and everything like that are all fun and good, but what we want to go and do is we just want to go and see how this would look in real life. So give me a second here, and I'm going to go and pull up a demonstration board. You can hear it bumping around in the background over there. Okay. All right. So here we are. What we have is we've got a demonstration board. So let's just zoom in a second. We've got a demonstration board over here that has got a number of nails that are placed into it, and you can see that the nails form a triangle, and we can see that there's a center nail over here as well that we can also go and utilize. These are going to go and become my points that I can build a circuit around. I'm going to have line, 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 and if my circuit has a neutral, I'm going to go and have a neutral inside of there. What we're going to do is we're going to start with this first example where they're showing us a Y type of system that does not have a neutral. And in order to do that, I'm going to go and use tension. And you should be familiar with the term tension, because tension is often used to go and describe voltage. We'll talk about things like the electrical tension or high tension lines. It's really just a force between electrons. And the best way to demonstrate that is going to be through the use of elastics. So over here, I've got 3 elastics and a rubber grommet, and I'm just going to go and stretch those 3 elastics out and across, and one of my nails just went flying out over here, out and across this board over here. And you can see that because we have got an equal amount of tension on all of these, that automatically the center is centering around that very center section over here. If this was a 122/8 system, that's why I've got these values off of here, we can see right now that I'm going to go and have an even 120 across my C phase, my A phase, my B phase. I know it's not black, but a black elastic over top of a black board just wasn't cutting it, so we're going with yellow for this one. And what we're going to do then is we are going to go and lose a line. Remember how I said each of these was going to be my individual lines? If you take a look at your example number 1 inside of your book there, they say we're going to go and lose line C. So when I lose line C, what do we see happen? Well, we see that line C has got no complete circuit, so there's not going to be any voltage that's going to be dropped across it. And I see that line A and line B snap directly across from line to line. Well, what's this line to line value? This line to line value is 208 volts from line to line, as well as from line to line. But now because I've got this Y connection where all 3 were connected in the middle and I lost that line C, all of a sudden now we see that these 2 loads are going to go and center themselves over top of 208 volts. And because they're equal values of resistance, if I've got 2 equal values of resistance, I'm going to be dropping 2 equal values of voltage. And if this is 208 from here to here, that would mean halfway down would be 104 volts that we would have. Let's go and compare that with what it shows inside of our book. Over here inside of the book, they show us this drawing over here, where we see that they still have kept all three of these together inside of the exact same, Y type of connection. It still looks like a Y over there, but we have actually lost some of our connection on one of our lines. Over here, we've opened up the line 3, our C phase over here, and as a result of that, we have now these values of voltage that are going to be changing. We no longer see 120 volts, we now see 104 volts and 104 volts. And this is exactly what we just saw where we had the triangle. We see that really these two loads are stretched across from there to there, and because this value from this line to this line is that 208 volts, therefore we are going to go and have 104 volts dropped over top of each one of these. Okay, that's cool for how we get to the values of voltage. Now what we want to do is we want to go and figure out a couple of other things off of here. We want to go and figure out what we would have for single phase power right now. And this is called single phasing, where we have lost our third leg and we are down to a single phase situation. These are each 10 ohm resistors. If you go and read inside of the question, we say that these are 10 ohm resistors each. And now that we are looking for our line current, well, if we take a look, since this line is now open over here, we can't have any current through it, which means that all the current has to come in on one line, has to go out on the other line, indicated by those two arrowheads that we have over there. So we can figure out exactly how much current we're going to go and have. If I take a look at this, remember we said that these two, because we lost that third line, we basically snapped those two across from point to point. And because we've done that, we now have got two resistances in series. Everybody knows how to go and add resistances in series. 10 ohms plus 10 ohms in series gets me to a total of, oh man, tough math over here, 20 ohms that we are going to go and have. 20 ohms of resistance, and how many volts is that going across? Well, we know what our line value of voltage is. That hasn't changed because our supply controls that. The load doesn't control the voltage. The load distributes the voltage, but it doesn't control what is actually fed to it. And we see that it's at 208 volts that we have over there. So what we can do right now is we can go and say, if I have got I that I'm looking for, I line, I can go and take my E over top of my R. 208 volts that we are going to go and have, divided by 10. 208 it's divided by 20 because it's the two of these placed together. 208 volts divided by 20, and we can go and punch that through on a calculator. We'll just do that. Gets us to 10.4 amps. So we have got a current traveling through here of 10.4 amps that we have. Is it a three-phase circuit? Absolutely not anymore, because we don't have that third line. So we don't have to use any of the root 3 or the 3 when we're looking at figuring out our total amount of power. We just have to go and use our volts and our amps. And we know what our volts are, 208 volts impressed across those two resistors. And we've got 10.4 amps that we have over here. If we multiply those values together, we've still got a 10.4, we'll just multiply that by 208. We end up at a value of 2,163 that we are going to go and have for a total amount of watts. The total watts of this system right now, and I'm just going to put that watts SP single phase, 2,163 watts that we have over here. How does this compare to what it should have been? Well, this is really the big thing about single phasing, is you want to know what is it supposed to be at, and what sort of an effect are we going to see, because the customer never tells you what's going on. They just say my machine is doing X or Y, and based on that we're supposed to figure things out. Let's just erase these and let's just go and calculate what this thing would be if we still had a good line going across there. If we still had a good line going across on C over here, we would still have this neutral point that would be stretched out to the center, or that point is not tied to a neutral, but we would have that point that's stretched to the center. Each of these values would be 120 volts, 120 volts, and 120 volts. And we know that because we have got a three-phase, but it's a Y, and we know that my E phase is equal to my E line divided by root 3. 208 is my line value of voltage. Divide it by root 3, which is going to go and get me to a phase value of 120 volts. And by now you should be starting to memorize this. 122.08, 122.08, 122.08 is just a common value that we are going to deal with all the time. Okay, so since we got that phase value of voltage, we could then go and figure out what we have for current going through each of these loads. If I've got 120 volts, and if this is a 10 ohm resistor over here, I can then go and figure out what my current would be through this phase. I phase is equal to my E phase divided by my R phase. Place those values in, 120, 10 ohms over here, and we see that 120 divided by 10 ohms is going to go and get me a phase current of 12 amps. So we would have 12 amps that would be flowing through here. That full 12 amps, there is no path for that 12 amps except to come back along the line. So therefore, because it's a Y system, I phase is equal to I line. So my line current would be, I'm just going to erase this one here. My line current, if the system was working properly, was going to go and be 12 amps. Now that we have got a full three-phase system working, all three of these lines are working here right now, we could go and figure out our total amount of power. And our total amount of power, since there is no power factor, it's resistive loads over here, would be my E line times my I line times root 3 is going to go and give me my VA in this case, and because it's all resistive, all of my VA is going to be watts. Let's go and punch those in with values we have. We know what our line value of voltage is. 208. We know what our I line is, 12. We know what root 3 is, that's 1.732. So we'll just go and put that in there. 208 times 12 times root 3 equals a value of 4,323. So my original original 4,323. What's the relationship between my original watts and my single phase watts? Well, to figure out your relationship, really you just need to go and take them and divide them. 4,323 divided by 2163, which, oh, wait for it, it's going to be amazing. 4323 divided by 2163 equals 1.9986. In other words, the larger the original is double. There's just a little bit of rounding error. That's why we've got all of this, 1.9986. But basically, I see that my original is double what I had when I went to single phase. Or I could alternatively say that when I'm single phasing off of this Y type of connection, I'm only putting out 50% of my power. This is the thing that your customer is going to go and tell you. He says, hey, I've got this, this machine. It was a big three-phase furnace that we have. My furnace isn't putting out full heat. It's just not coming all the way up to temperature, and I don't know what it is. Can you come and fix? As soon as you hear that it's not coming up to full temperature, you know that you have lost a line in there somewhere. There's a good chance that that thing is single phasing. The next thing that we're going to look at, though, is going to go and be a three-phase AC supply where we are going to go and put in a neutral. This first one that we looked at over here did not have a neutral connection. We had connected all three of our loads together as a star point, but we didn't have an actual true neutral that was going to come back. Do you remember how previously I said the neutral stabilizes voltages? We're going to go and see that now in our very next one, because in our very next one, they say, hey, what if we took the exact same sort of circuit and we put a neutral on? What is going to go and happen? Well, let's go and take a look at what would go and happen if we go and stabilize. Once again, we're back to this handy dandy little piece of wood, and we have got our three lines over here, as well as we've got another nail that we are going to go and use as our neutral. We're going to connect these elastics across, and across. We see that when we go and provide tension lines, that it is going to go and stretch it out. And so we end up with this Y type of shape. It's just electrical tension that's holding our loads, in this case, the elasticity across there. But now what we're going to do is we are going to go and insert a neutral. We're going to tie this thing to a neutral over here. So I'm putting a nail in the absolute center right now. What the neutral does is it stabilizes stuff. We've said this so many times, but you just have to be aware of the fact that it does stabilize. And inside of your problem, the open line with a neutral connected to the load, watch what happens when I go and lose my line. They show in your example that we're losing line C. As soon as I lose line C, because we've got that neutral connection, do these two change? Absolutely not. You can see that they're still stretched out over there, which would mean how many volts is still across each of these? It's still going to be 120 volts across this one and 120 volts across this one. So this resistance here is going to get the same full voltage that it had before. This resistance here is going to get the same full voltage that it had before. This one over here, because it's open, is going to go and have 0 volts across it because there's no complete path for current, so therefore we cannot go and drop voltage across it. That's pretty cool. It's the stabilization of the neutral. Let's just try it one more time without the neutral inside there. If we don't have a neutral, I'm just going to pull the neutral out. If we don't have a neutral and all three of my lines or loads are good, we're fine. But if I don't have a neutral and I lose a line, we see that the voltages across these change, right? They get smaller. They're no longer going to be that full 120 volts that we would go and have across it. As soon as we put that neutral back in, one more time over here. As soon as we put that neutral back in, and if we lose that line, we see that these two loads are unaffected. This is what we mean by stabilization of our voltage that we are going to go and have. Okay, going back now into our drawings over here. We have got these same ones that we have to go and look at, the exact same ones that we had there before, and we are going to go and use the exact same resistances, 10 ohms over top of here, 10 ohms inside of here. And we saw that we lost this line over here, but we see that because we have that neutral, that anchor point inside of our circuit, that we're still going to go and maintain the same 120 volts over top of these. So I can figure out my phase values of currents. I phase is going to go and be E phase divided by R phase. We've done this calculation before. E phase is going to go and be 120 volts. R phase is going to go and be 10 ohms. I don't know what I'm writing over there. 10 ohms, which means that my current is now going to go and become 12 amperes. So I can go and say that my I phase is equal to 12 amps. The beautiful thing about watts is that watts don't lie. So I'm now going to be able to go and figure out the watts of this system and the watts of this system over here, and I'm going to be able to go and add them together because watts plus watts equals watts, just more watts over here. So let's figure out what our individual watts are going to go and be. Just give ourselves a bit of calculation room over here. I know that I have got 12 amps, and I know that I have got 120 volts. Watts are equal to my amps times my volts. So 12 times 120 is going to go and give me a value of 1440. We can just punch that through over here. 12 times 120 equals 1440. 1440 watts that we have for this resistor. And then for this resistor over here, which is also operational, we are also going to go and have another 1440. And if I were to go and add those together, 1440 plus 1440, it's going to equal 2880 watts that we are going to go and have. Do you remember the previous calculation, how much this thing was designed to go and run? It was designed to go and run 4,323, but right now we are running 2880. We can figure out what percentage this thing would be out of that by just going and dividing that. 2880 divided by 4323 there. And when we go and do so, 23 equals 0.66620, etc., etc. Once again, a little bit of rounding error that we have inside of here, but we should recognize 0.66 repeating like that as being 2/3. In other words, what we see over here when we have got the neutral, the anchor, so critical. Once we've got that inside of the system over there, even if we go and lose a line over here, we lost that line, we still put out 2/3 of our power. So 2/3 power with the neutral, 2/3 power with neutral, half power is what I go and put out anytime that I have got the without neutral. So I'm always going to have a little bit more stability off here. The other beautiful thing is if I had differing values of resistance, those differing values of resistance, if I don't have the neutral, are going to go and readjust to go and form different values of voltage. Right now we had 104 and 104 over here based off of the fact that they were equal values of resistance. But if one of these, let's say that the A1 was a higher value of resistance, then we would have a higher value of voltage. In fact, it could be over 120 volts, it could be 150, 170, which on a 120 volt load is not going to go and be good. Whereas this type of a system over here, if this one was a higher value of resistance, as long as we've got that neutral connected, it is still going to go and maintain that 120 volts across it. Safer stabilization of voltage, and it's going to be stabilization of my just of my system itself. Last thing that we have to go and look at over here is just going to be the amount of neutral current that we are going to go and have. If I had my lines good, so if C line over here was fine, we would then have 12 amps, 12 amps, and 12 amps, and we've done this calculation in the previous video where we saw if all three of our line currents were the same, that the net current would have been 0 amps that we would have had on there. But at this point, once we lose that line over there, this changes over here on this line. This line before was acting as a true neutral. Now it is acting as a common because it's only carrying 2 lines. And if I go and add up these two, we did that calculation for a common as well. We could just put these in at an angle. We'll put this 12 at angle 0. We'll put this 12 at angle 120. If I would go and add those two together, I would come out to a total value of 12 at angle 60, lying halfway in between that. In other words, whenever I have got a neutral in play, but I lose a line, I'm going to go and have neutral current. Once again, really easy to go and take a look at. Your customer is going to phone you. Your customer is going to say, the heaty thing is not making the heats. And so you're going to come down there, you're going to stick your clamp on ammeter around the neutral. And if it was a 3-phase heater, you should have 0 amps coming back along that neutral. But as soon as you see currents coming along there, you've lost one of your lines. You take your clamp on ammeter, you stick it around line 1. Yep, 12 amps. Stick it around line 2. Yep, 12 amps. Stick it around line 3. Hey, no amps. Therefore, this line over here must be incomplete. It could either be the load or it could go and be the line itself. All right, cool beans. Let's move on to the next one. The next one that we are going to go and take a look at is going to go and be what would happen if my load would be the component that would go and die. Okay, if my load is going to be the component that is going to go and die over here, it is going to go and interrupt. Take a look. This is really just the same line all the way along there. So whether that line would go and open over here, here, or in the middle of the load, it is either way going to sever the current and it's going to go and do the exact same thing. What we're going to go and see is we are now going to go and see a load that is going to have a voltage dropped across it. This is what's changing over here. When the load opens, I see a higher value of voltage over top of that load. Before, when my line opens, let's just go down to this one over here and let me erase a pile of that. Before, when I had an opened line, I saw that I had small voltage over the 2 remaining ones, and I had 0 volts because there was no complete path across that load, because the open was way further upstream. over here. But now what we're looking at is we are looking at the load actually opening. We're going to see the same small values of voltage over here, but now I'm going to go and see a larger value of voltage that is going to be seen across that load itself. Once again, let's go back to our demonstration board over here. Right here on the demonstration board, we've got that same system where we have got, first of all, we're working off of figure number 4 where we don't have the neutral connected to anything. So I can see that this thing can move around, but because I've got an equal value of voltage, tension across equal loads, it's automatically going to go and center there in the middle. What we can do is we can open our load. Now, if you go and refer to your book over there, you're going to go and see that it's going to be your load number 3 that is going to go and open. As soon as we open that, we see that these two snap back across here. Once again, we said this was 208 volts from line to line over here. Because we have now opened that up at the 208 volts across there, these are now going to be centered across the middle, which is going to be 104 that we are going to go and see across either one of these. This over here, just give me a second, we just need one more piece. Because the load is open, I'm just going to hang a little piece over there. That means one end of the load is still connected to the line still exists over here. The other end of the load is connected across to the center point between these other two over here. So really when I'm measuring across this load, I'm measuring across this span that goes all the way across over here. And if you were to go and take a look at this, span, how far is it? You could go and figure this thing out just by using simple trig. If you take a look, it would be a right angle triangle going across like so. And we would know that this line here would be 208. From this point over to this point, it's 208. We would know that from here to here is going to be 104. So just do straight Pythagoras. 208 squared minus 104 squared. Take the square root of all of that. That's going to tell you what you're going to have left across here. And that value you're going to have left across here is going to go and be 180 volts at this point. Let's go back and take a look at that over here. Off of my pictures, we see that we have got this 180 volts. They show us the way that they summed that all up, the vectors over here. Remember how we said that, look, we're going to go and have one resistance across here, one resistance across here, across the existing lines. Therefore, we had the 208 that was divided in half, and so we just had this line over here, and really we're calculating this triangle. And because we know this value is 208, and because we know that this value, half of that one, is 104, we're able to go and calculate that triangle over here, 208, 104. Pythagoras the crap out of that thing, and you are going to go and end up at a value of 180 volts. What's significant about this is not so much that it is 180 volts. It's going to go and change between them. But what I'm going to go and see is I'm going to see a value of voltage when I've got an open load. There is going to go and be voltage across that load. And that voltage that's going to be across that load is going to go and be smaller than E line, but it is going to be larger than E phase. That's all that I'm looking for. So if I run into this situation where I have got a single phasing load right now, and so we just did this one here where the neutral was not tied in, and I get my customer is going to go and phone me up. Is there going to be any watts dissipated by this resistance heater? Absolutely not. There's going to be no watts because there's no complete path of current flow. Therefore, we cannot go and bump electrons and create heat. So since I'm not going to have that, I'm going to be down to just these two. We already determined that during single phasing, we are getting half watts, half of our power that we are going to go and have out of here. So my customer is going to go and phone me. The customer says, hey, I have got not very much heat coming out of my furnace. Can you come down and check it? I'm going to go and check my furnace. When I measure across my elements, I see low phase, lower than phase. I see lower than phase. And then I see one that is going to be in between my line and my phase value of voltage. And because it's in between my line and phase value of voltage, I know that it's the phase, or that it's going to be an open inside of that phase. Compare it to this situation, this situation over here, where I know that it's an open line, and the reason I know it's an open line is because I have got 0 volts across a load and low volts across the other two. So 2 lows and a 0 is going to be an open line. 2 lows, 2 lows and a high, so 2 lows and a higher value is going to be an open load. Keep those two separated. From there, you should be able to, just off of a couple meter readings, really quickly be able to go and figure it out. You'll also be able to figure out questions when they come to you on exams, IPs and stuff like that, because anytime that I see 3 values of voltage, I know that I've got some sort of an issue with my actual loads. As soon as I see only 2 values of voltage, I know I've got an issue with my lines. Okay, last one that we have to go and take a look at is what would happen when we get an open load in a circuit that has that neutral. Once again, we're going to go back to our system that we had here. Let me just go and pull this one off because we're no longer using that. We're going to go back and put on another set of elastics over here. We're going to phase and a phase and a phase. So we stretch it across all 3 phases, and then we're going to go and connect it to neutral, which means I'm going to go and connect a line inside here, which means that now I have got my anchor point. Stabilization of voltage. So critical. Okay, and now we're going to go and open a load. Well, if you go and refer to your figure 6 inside of there, it says what's going to go and happen when I get an open load with a neutral connected. If I get an open load with a neutral connected, let's go phase C over here. Oh no, dull knife. It's nowhere near as dramatic as what it was supposed to be. We will get the scissors out there. We see that as soon as I cut, or as soon as I open that load up over here, I see that this load stays unaffected. I see that this load stays unaffected, but I see that this load over here does not have a complete path for current flow, right? I've still got just a little bit of blue over there and a little bit of blue over here, but there's no complete path for current flow, therefore we're not going to have any watts that are going to be dissipated across it. This one is going to dissipate full watts. It's still got the proper value of voltage over top of it. This one's going to dissipate full watts. It's still got the proper value of voltage across it. This one over here has got the proper value of voltage across it, but no complete path. So I'm going to go and have a situation where I'm going to get 2/3 of my heat, 2/3 of my elements are working, and I'm going to get full value of voltage, phase voltage, across each of my windings. This one here is going to go and have a full value of voltage across it, but it does not have current going through it. The other thing that I'm going to note is that because I've got my neutral connected, if I would stick an ammeter around my neutral line itself, now I'm going to have current coming back along that neutral, because that neutral is no longer truly a neutral. It has now turned into a common because it's only got 2 lines that are tied to it. We see that inside of this one over here. Once again, it's going to be that Y type of connection that has, that has got proper value of voltage over top of all 3 loads over here. We're going to be dissipating 2/3 of my watts, but now I'm going to go and have current along my neutral. I'm going to go and know that this one is an open load because I see this value of voltage that is placed across it. Let's just go and compare that with when I've got a neutral and no, let me just erase a bunch of this over here. When I've got a neutral, but I open inside of the line, a line open is going to go and give me 0 volts across my element over here. These other 2 still have proper 120 volts. As soon as I have a load open, I'm going to go and have proper 120 volts across the operational ones, a full 120 volts across the open one, but now I'm going to go and also have that common current that's going to be coming back along my neutral. In this case, if these were each 10 ohm resistors, we would have 12 amps coming into each of my lines, 12, and I would go and have a common current of 12 amps coming back out as well. Okay? Keep those all straight. If we've got a neutral, we stay at 2/3 of our power. That's just, the long and short of it. If the neutral is in there, the other phases are unaffected, and we continue to go and put out 2/3 of our power. If we don't have a neutral inside of there, we put out 50% of our power. And anytime that it's an open load, there's always going to be a voltage measured across the load. Anytime that it is an open line, there will be no volts measured across one of those load components. All right, that's it for our whys. We're going to go and take a look at deltas in the next video.